Greetings, mathophiles, and welcome to the second of two videos on what's known as the mean value theorem from calculus. In the first video, we made sort of a graphical exploration of how it works. We stated the theorem formally, and we worked through an example. In this video, we're going to take a look at a couple of situations where the conditions for the theorem are not met and see how that might lead to a situation in which the conclusion is not obtained either. You'll see a statement of the theorem on the screen, and you'll see that the two conditions we need to be interested in are the continuity and the differentiability of the function in question. And so our two examples in this video will involve, first, one in which the function is not continuous, and second, one in which the function is continuous but not differentiable. You'll see on your screen the function f of x equals 1 over x minus 3 quantity squared. So it's 1 over x squared translated 3 units to the right. And we're going to examine it on the interval 9/4, 7/2, or from x equals 2.25 to x equals 3.5. And so you see on your screen the secant line connecting those 2 points on that interval. If I turn on a tangent line that is movable by means of a slider, the conclusion of the mean value theorem would require that this tangent line be parallel to the secant line somewhere on the interval. However, as we move this tangent line around, you see that at least so far it's not parallel to the secant line. I keep moving it and moving it and moving it, and I just don't see that. Here we are over on the other branch. And we actually do reach a point where the lines are parallel. But the problem that we face, or at least the thing that we observe, is that the point of tangency is not on the interval. So the condition of continuity was not met, and we see here that the conclusion of the theorem is not obtained. The tangent that is parallel to the secant line is parallel at a point that is outside the interval. Let's take a look at how this plays out algebraically. We have our function on our interval, and if you plug in the x values at the endpoints, you get 16/9 at x equals 9/4, and you get 4 at 7/2. And if you run that through your rise over run, you get that the slope of the secant line is 16/9. So if the theorem were in play, if the mean value theorem were in play, we would need it to be the case that f prime would be equal to 16/9 someplace on the interval. And as we saw graphically, that is not going to happen. Here's how it works out algebraically. F prime of x is -2 over x minus 3 quantity squared. There's no chain rule there, so it's just basically a power rule with a negative exponent. And so we would need -2 over x minus 3 quantity squared to be equal to 16/9. Which means we would need x minus 3, that's my bad, that's a cube. We would need x minus 3 cubed to be equal to -9/8, which means x would be 3 minus the cube root of 9/8. And that is approximately 1.960. And that is not in the open interval 9/4 to 7/2. So the hypothesis of one of the hypotheses of the theorem was not satisfied, and the result does not obtain. Now, it may be the case, depending on the circumstances of an individual function or an individual interval, that even when the hypotheses of the theorem are not satisfied, you might still see a situation where there was a parallel tangent to the secant on the interval. But it is not required, and as we can see here, it certainly can fail to occur. You need to be a little bit cautious, though, just speaking practically if you're a student in a calculus class, because you can work through the process and get an answer. We have a place in this example where the tangent is parallel to the secant. It's just not on the interval. Here is our second example. This is the function y equals absolute x minus 3 minus 5 on closed -5, 7, And you see here the graph of the function and then also the secant segment as belonging to the secant line. If I turn on a tangent line and I begin to move it around a little bit, it becomes readily apparent that the tangent line is going to coincide with the function on each of its branches, if you will, on either side of the vertex. And in fact, at the vertex, at x equals 3, the function is not differentiable, and thus there is, I'm having trouble getting it, there we are. The function is not differentiable, and therefore there is no tangent line. So this is an instance of a function which is, although it's continuous, it's not differentiable. And as you see, there is no possible way graphically for these tangent lines to be parallel to the secant line. It's just not in the cards. As we did with the first example, let's take a look at the algebra of this one. So we have our absolute value function that has been shifted 3 to the right and 5 down on the closed interval -5, 7. You plug in the -5 and the 7, and you get the relevant function values, the y-coordinates of the endpoints of the secant segment. And if you do a little algebra 1, you find that the slope of that secant segment is -1/3. If we take g prime, we find that it's absolute x minus 3 over x minus 3 plus 0, no chain rule. And this in turn is either 1 or -1, depending on where we are. It is 1 for x greater than 3. It is -1 for x less than 3. And so if we try to set g prime equal to the slope of the secant, we are in deep weeds because this is only ever 1 or -1. Neither of those, of course, is equal to -1/3. So in this case, we don't even get a parallel tangent to the secant outside the interval in question. We don't get one ever. I hope it's been helpful to see a couple of examples in which the assumptions of the mean value theorem are not met and how that plays out in terms of whether the conclusion is maybe a possibility or not. It's a good way of getting a little deeper understanding of the theorem. It's also a good way to be sort of warned that you don't want to go charging in, applying it in situations where it is not legally available. So, hope it's been an aid to understanding. Happy mathing.